I'm intending to talk about bosonic coding, but because there will be other speakers talking about basic quantum error correction and not just bosonic error, other aspects of quantum error correction, I'm going to spend probably the whole time in this first lecture just introducing basic quantum error correction. I sampled you all, and it seems like the level of prep is all over the place, so I think it's good to go through the basics before we specialize to bosonic coding. So what is the goal of error correction? And this is true for both classical and quantum. We come back to our old friend Shannon, who brilliantly sort of just started this whole field out of nowhere. The goal of error correction is to preserve messages sent through a noisy transmission channel by encoding the messages in what's called an error-correcting code. You want to think, naively, you want to think of an error-correcting code as a way of encoding information redundantly in some system. However, the more enlightened version of the definition of a code is philosophically an entire protocol that is designed to not only encode but transmit and also then extract or decode said information. So another more precise way of looking at it is of the goal is to make sure that the rate of corruption of the encoded, or in other words, also known as logical information, is lower than that of the same information sent without the extra encoding step. So let's start with a message row. And again, I want to emphasize this message can be classical or quantum. This type of Shannon framework holds for both. And to utilize an error-correcting code, we then apply a map, what's called an encoder, to this message. After we've encoded it, we send the message through a channel. And the channel is noisy. The noise here is not some adversarial Eve that everybody likes to talk about in crypto. This is more sort of environment imperfections in your fiber, things that we haven't things that we can't really control. But it's not some bad person inside the wire trying to hack your signal. Now, what's interesting about how general this framework is that this noise can be space or time-like. And by that I mean, one example is that we're sending information through a fiber, which is going through space. And another example is we're storing this information in a hard drive or an electromagnetic cavity or anything stationary in space, and we're storing it in time. Okay, so this noise channel can be parameterized by space or time. And then on the other end, okay, Bob, if you want, will want to extract the information that was sent to them. And that is done using a decoder. The noise will perturb the information, will cause the message to sort of be smeared out in a way that it was not initially encoded. And the job of the decoder the hard job of the decoder is to extract this as much of the message as possible. So in the end, what we want is we combine all these three maps, and we basically want it to be as if the noise was never really there. Okay, so the D basically eats the N. Okay, and I purposefully put the approximate equal sign here because this is never going to be exactly equal in the real world. Okay, no matter how nice your examples from many of your previous error correction courses were, real noise is never going to be exactly correctable. Okay. So our best there's going to be some measure of approximateness here that we have to deal with. So this is basically the whole purpose of error correction. And applications are fairly wide, starting from the initial 70-year-old framework of Shannon theory. We have your classical error correction used in hard drives, USB, what is it called? Wideband streaming or satellite communication, cellular communication, other different wireless protocols. And then, of course, on the quantum side, you have this grainy picture that I should have probably attributed somebody with. you have your quantum computers, your quantum memories, quantum hard drives, and then you have quantum communication or transmission of quantum information over links.
Yeah, I have a question. Why did you write DE rather than just row?
Just to emphasize that, I could have just written row. I just wanted to emphasize that the decoder is sort of trying to eat the noise. This will be useful for the next equation I'm going to show, which is going to describe something that's more complicated than error correction, that requires error correction, but for which error correction is not sufficient. It's called fault tolerance. Who's heard of fault tolerance? Notoriously hard to define, okay? And I'm going to give you a little bit of a philosophical sort of heuristic view of it, okay? It's not going to be super rigorous here, and this is the reason I wrote that here. So fault tolerance deals with an extra layer of complexity that we've added to our problem. We are no longer just interested in transmitting the information, we're interested in applying some sort of operations on the information, okay? Now, in classical coding theory, fault tolerance is not super widely studied because it's not really necessary. The noise there is not so bad, and we can more or less do our computations, and our hard drives are pretty stable. But for quantum information, quantum systems are sufficiently fragile, the environment is sufficiently noisy, so as to making us have to care about specifically how we do our gates, okay? So the study of fault tolerance deals with trying to successfully apply operations. In this case, we have a new letter here, G, on the message within a noisy environment, right? Because when we apply our gates, our environment doesn't go away. Our hard drive is still subject to some quantum noise. And one way to sort of see what a fault-tolerant gate G is supposed to do is the following equation. So let's say we've encoded our information, we have some noise channel, and then we want to apply this gate before we extract the information. So this is maybe Shor's algorithm or what have you, QAOA. And we want G to be fault tolerant. What does that mean? That means that G should not change or amplify the noise in a way that the noise now becomes uncorrectable. So here, this N was eaten by the D, okay, for all row in the code space. But now we want to test that G doesn't change N into some N tilde such that N tilde is severe enough that D can't swallow it, okay? And this N tilde is just nothing but the original N conjugated by G, because I have assumed G is reversible. Okay, so I've just permuted G through, and now I have a new N tilde, and the goal, so for G to be a fault-tolerant gate, basically this needs to happen. Again, this is heuristic, because fault tolerance is kind of difficult to pin down, but this is the whole point. So does this make sense? The G needs to make sure, we need to make sure to do a G such that it doesn't amplify correctable noise into uncorrectable noise.
You know, I still find it difficult. I mean, all of this could be satisfied if D is equal to 0.
If which D is equal to 0?
Yeah. It just has to equal nothing. 0. 0.
Well, so I'm assuming that this is a map that preserves the structure of the message. So for quantum systems, the D is a channel, is a quantum channel, completely positive trace preserving map.
Well, let's suppose that it takes any destination to the fully mixed state.
D.
Yeah.
Okay, yeah, that's fine. That's fine. Yeah. But then you haven't, yeah.
I mean, there must be another requirement.
Okay. Oh, I see. So you caught me here.
Yeah.
If this was row,
Right.
fine, okay, yes.
Yeah, but how does the difficulty is that while encoding any noise, taking into quantum
Yes.
so it's like if you go around it by relaxing it and saying that I think 85% correct, if I encoded and decoded into noise.
No, I'm assuming noiseless encoder decoder for now. Yeah, it gets even crazier as you're beginning to see if you say that none of these operations can be performed perfectly. All right, and then there's another, so there's layers and layers of things, okay, here. I'm just assuming everything's perfect and then I'm applying noise. So good, right. So D, what property? Yeah. The yeah, so how am I supposed to reconcile it? Yeah, probably. Or I'm thinking maybe I could, on the spot, think of some conditions on D such that this particular situation that trivializes the whole transmission protocol doesn't apply. But for sake of simplicity, okay, it should be rho here. Yeah, I should just put rho here and not bother. But okay, yeah, this was just to emphasize sort of this part. Okay, just a little bit of history. So classical error correction has been around for 70 years, ish. And it wasn't clear once people started to think about quantum information theory that you could even do similar things with quantum information. And Peter Shor was, I think, the first one to actually show by constructing a specific quantum error correcting code, which we'll describe later, that does successfully protect quantum information against some noise. And then all sorts of other protocols started to come up. Alexei Kitaev made the connection between error correction and condensed matter by developing a particular series of codes that are based on things called anyons. Who's heard of those? The physicists raise their hand. Yeah. Won't be getting into that today, but very important discovery as well. And this led to the surface code, which is, as you know, the prime candidate, at least for some companies, and things that people spend their whole lives studying. Of course, there's other pioneers, and let me just do this sort of obligatory, if you Google quantum error correction, then you see that more and more papers are beginning to happen here. Especially, I think this is in part due to the fact that engineering has caught up, and people have started to realize a lot of these codes and protocols even. I'm going to do an introduction to quantum error correction using the most basic code I could find. Okay? And then we're going to make connections between said code and bosonic codes and other codes that you probably will find in Anthony's talk. So the goal, so a code, again, this is the specific sort of mathematical definition. A code is a subspace of a quantum system that is chosen in some clever way as to protect against some noise channel. So let's consider the simplest code, the repetition code, and this code is designed to protect against what's called, the jargon is bit flip noise, but it's just sigma x acting on one qubit. So a code is a subspace, so what do we use to define a subspace? We can use a basis to define a subspace. And the basis here is in this 3-qubit space, so there's 8 different states, and the first basis code basis element, or code word, is the 3 qubits being in the all 0 state. This is called the 0 logical code word, and the 1 logical code word is all 3 qubits are in the 1 basis state. Now, what is quantum information as opposed to classical information? This is important. Let's just go back to the basics here. In classical coding theory, using this code is a classical code. Using this code, you would send, if I flipped heads or tails and I wanted to send that to you, I would send, if it's heads, I would send you 3 zeros, and if it's tails, I would send you 3 ones. And that's classical information for you, okay? One of the code words is sent through the channel. In quantum, superpositions of code words are sent through the channel. We want to protect quantum superpositions of what used to be our classical code words. And quantum superpositions, have these complex coefficients, and this is the information we're trying to protect. So we're trying to protect superpositions of vectors. And so the most general logical state here in this code is just a logical qubit's worth of quantum information. Now, what happens now when we send it through the channel? Let's say we had an error happen in the channel on the second qubit. The second qubit was flipped. So that means we're here now, right? Okay? And what what are these? So what is the result here? Well, the result here is that we've actually gone to a different set of states here than here. These states are orthogonal to these states. And these are called error words, and this is called an error space. And this is exactly the point of error-correcting codes. Because this error has caused us to go somewhere else, you can use already basic quantum mechanics, no jargon, no nothing, to tell me right now whether or not you can detect this error. Now, this error has taken us to a different subspace of the system than the original subspace in the information. And moreover, it has mapped us isometrically in this subspace, which is just fancy for this superposition has been preserved. It's just now a superposition of different vectors. Now, using basic quantum mechanics, you can tell me that there exists an operator that can be measured, that can resolve the two subspaces without resolving the information within each subspace. So this operator, or operators, are sort of like a good set of quantum numbers, if you remember old school quantum, but they're not too good because you don't want them to resolve information, the quantum information itself. You just want them to tell you which subspace they're in, the information is in. And this happens whenever the error space is orthogonal to the code space. So the two spaces here can be distinguished without collapsing the logical information within them, right? Let's say the operator is +1 here, and -1 on these states, and whatever on the other one, some other eigenvalues. And this means that this error is detectable. And this basic fact, again using basic quantum mechanics, is a sufficient condition for any error taking information out of the code space for any error-correcting code. Okay? So if there's anything you want to get away from this, that's sort of one of the simplest things, but is fairly ubiquitous, is this type of idea. Let's go into a little bit of the detail of how to do this, what I just said, basically. Again, I used basic intuition from quantum to show you that in principle this is possible, but now let's say how to do it. So we want to resolve the code and error spaces in order to detect our error. The jargon for this is called error diagnosis. There's a lot of medical terminology coming in now. We want to measure some sort of operator, or in most cases, we need to do multiple operators. And these are called check operators. Okay? And then we want to, once we figured out where we are we in the code space? Are we in an error space? Then if we're in an error space, we want to go back to the code space, right? Because we want to apply what's called a recovery. And the good set of, the not too good set of quantum numbers that labels our error spaces are called syndromes, or error syndromes. And together, this whole process is called one round or one cycle of error correction. So here we go. So here's our 3 physical qubits, the ones where we have our subspace. And here's the circuit for extracting the check, for extracting the syndromes. And these are called C0 gates. Everybody know what a C0 gate is? I can, yeah? Okay, good. So this C0 gate just takes its conditional flip of this. These are called ancilla qubits, conditional on whether this is in a 1. So if this is in a 0, this does nothing. This is in 1, this flips. And then this gate does the same conditional on this qubit. And so if both of these are in 0, nothing happens. If both of these are in 1, nothing happens because things add mod 2. However, if one of them is in 1 and another one is in 0, then this qubit goes from +1 to -1. Okay? And so you see, and then you measure this here at the end, and you get a +1 or -1 depending on whether the first 2 qubits are equal or not. This is your syndrome. Okay? And this is equivalent to measuring the eigenvalues of ZZI, where Z is sigma Z, Pauli matrix on the first qubit. Same thing happens here for the last 2 qubits. Okay? And so we have, right, and then we do, then conditional on the syndrome, given a particular set, whatever, ±1 for each of the 2 syndromes, then we apply some sort of operation, U, that depends on which syndromes we started. Determining which U to apply is called decoding. And is decoding hard or easy? Computer scientists, is it hard? It's hard. And you can ask me later why it's hard. For us, it won't be too hard because we're doing bosonic codes. But in general, it's hard if you scale up. Here, it's not so hard because we just have, stuff we can run on our laptop. We have just 4 syndrome outcomes here, and they correspond. So we have 4 syndrome outcomes, and we need to pick what we need to do here. And luckily, because we're using Pauli matrices, our errors are, if we just apply the error once more, we get back to the same thing because Pauli matrices square to identity. So we just have to figure out what to apply here, and we just apply the most likely error. Now here we assume that errors on few qubits are more likely than errors on many qubits. And if we do that, which is called a maximum likelihood decoder, some more jargon for you, then we just have 3 single qubit errors correspond to the 3 syndromes here. So for example, if you have -1 for the first 2, that means these 2 weren't equal. And if you have -1 for the last 2, that means these 2 weren't equal. Well, to reconcile both of those, the only thing that could have happened if we assume a single qubit error is that the second qubit was flipped. Okay? And so we just apply that operation again, and that corrects us back. Okay? Now, this is probably, maybe for some of you this is trivial, but this is, again, ubiquitous. This type of extraction, the idea that you extract just enough information to learn about the space you're in without resolving your quantum information, holds for all good, well-defined quantum error-correcting codes. Same type of protocols apply for all of these other codes that I'm going to discuss and that Anthony's going to discuss. We just don't, I just don't want to get into these things because there's already a lot of stuff I have to do, even for this fairly trivial majority vote example. Okay? So the reason this slide is here is because this is demonstrating a process that holds for all reasonable codes. And this round of correction needs to be applied periodically, because if we leave our information alone in the channel, then there's going to be noise, okay? And this round needs to be applied before the noise gets too bad. If we had, for example, 2 qubits flip, then this type of round will give us an error, okay? And so we need to make sure that these things are applied fast enough so that the noise the uncorrectable noise doesn't appear and corrupt our system. So there's a lot of overhead here, right? If I just sent 0 and 1, I didn't have to do anything. But here I have to constantly do something to preserve the information. I can't let the channel get too severe. Right, so that was a classical code. And now we're going to do our first quantum code. Why do we need to change classical coding theory? Well, it's because we're preserving quantum information. And quantum information gets corrupted by yet another type of error called a phase error, demonstrated here using sigma z acting on the first qubit. Remember, this is all one state, so this spits out a -1, and this -1 now so why is this -1 so bad? Well, does this error take my information out of the code space into an error space? Yes or no? No, right? And so do I have a way of detecting it? No. Because if I try to detect it, well, then I have to basically collapse my logical information to detect it. So I cannot detect. I can only detect on the level of spaces, because otherwise I'm collapsing logical information, and I want to store that. So I cannot detect it. And the next question is, well, if you can't detect it, it better have not done anything bad. Did it do something? Did it change my quantum information? Yes, it did. So it's something I can't detect, and it did something bad. That means it's an uncorrectable error. So we need to upgrade. So the simplest code that we're going to use here to just demonstrate the sort of the details of this is the 4-qubit code. So now we have 4 qubits, 16 possible states, and now here are our 2 basis elements or code words to define the logical space. And now notice what's the difference here is that we have the logical basis states themselves be superpositions of bit strings. And this is what is the key thing here that allows us to protect against phase noise, as you'll see. Before we get to the phase noise, however, let's check that we're still okay against bit flips. Okay? So single bit flips are still detectable, as some of you may already be seeing if you look at the Hamming weights of these bit strings. And single bit flips change the Hamming weight by 1 at most, and the distance in Hamming weight, the Hamming distance between the bit strings on one side and the bit strings on the other is greater than 1. That should give you some hints. But let's look at it in more detail, because you think this is trivial, but it's not. Let's look at the first qubit, noise operator. The first qubit here is flipped. So if we write this down, we go to these states. Are these states orthogonal to the code space or not? Yes or no? Yes. Can we detect this error? Yes, because we have gone away from the code space. We've gone away in a way that preserves quantum superpositions, or at least doesn't act on them in a way that we can't reverse them. Okay, so let's call these states 0x and 1x to contrast them with 0L and 1L. We have to check single bit flips on all the qubits. Let's try the second qubit. So here, if we write it down, now we get this. And now if we look carefully at these states, we see that these states are actually the same as these two states, but flipped. Okay. So can we detect this error? Yes. Why? Because we left the code space, right? That's all we got to do. We leave the code space, we can detect it. But we don't only want to detect, right? We want to also be able to correct. Can we correct these errors? Why not? Don't know which one comes back. Good. So how do we correct? Well, we have to pick a correction operation. We pick this one, then this is going to be bad. It's going to lead to a logical bit flip. We're going to go back in a reverse way, and vice versa. So we can't simultaneously correct these two errors. Good. And right. Okay. So let's now. So these errors are detectable but not correctable for the 4-qubit code. Let's do phase flips. Again, let's phase flip the first qubit. And so that means this one is going to throw some minus signs over here. Is this detectable? Yeah, because these are different states. Okay, actually, important. Why are these different? Because minus superpositions are orthogonal to plus superpositions. Now you start to see why superpositions are necessary in the code words, just to be even to detect it. Because these phase errors don't change the configuration space label, the bit string itself, they just induce signs. And so to make sure we can detect, we need more points in our code word constellation. Okay, this is the same thing happens here on the second qubit if we do the second phase flip because they're the same, these are the same, okay, because of symmetry. So let's look at the third and fourth qubits. If we do the third and fourth qubits, then if you do this carefully, then you notice, again, these states are the same. However, this one now is minus this one. So are these errors both detectable? Yes. Did we leave the code space? Yeah. Yes? Hearing? Okay. Yeah. Good. But now, how do we correct? Well, if we try to correct this one, we just map 0z to 1z, sorry, 0z to 0l and 1z to 1l. But then if this one happened, then we're going to get an extra minus sign, which is called a logical phase flip error. Okay? If we do induce the minus sign, we map 1z to minus 1l, then we're going to get an extra minus sign here. Can we resolve these two errors? No, because they both take you to the same error space, but they do a different effect. And that means they're not correctable. And if we now consider this combination of bit and phase flip, which is basically the sigma y error, the same type of thing happens. I'm not going to run that one through. You just have to believe me. And so what the conclusion here is that all single qubit Pauli errors are detectable but are not correctable for this 4-qubit code. Okay, that's great. But are all errors single qubit Pauli errors? I mean, we could have some crazy errors, right, in our channels. We don't have good enough control to just have everything to be single qubit Pauli errors. So is this a problem? Well, here's the sort of where one of the magic things come in. This is probably, I think, maybe one of the few, maybe the only instance where the collapse property of quantum mechanics actually helps you and doesn't hurt you. So when we measure these check operators, we're measuring eigenvalues, and when we measure an eigenvalue, we collapse into some particular error space or the code space. And that's the first fact that I want you to use to think about. And the second fact is that the Pauli operators, together with the identity, provide a basis or an operator basis, a way to expand all single qubit errors. And this together implies that general errors are actually detectable. So let's look at this for example. Sorry. So here's, just to review, here's our error spaces that we looked at. We have the code space, so you can fit logical information in here. This is two-dimensional. Then we have our 0x1x, 0z1z. Then we have some other error spaces that I didn't cover, but they're there. Okay? So a code basically provides a good code, so a code that allows you to figure out how to detect it, defines not only the code space, but also provides a partition of the Hilbert space in these nice Lego blocks and a set of not too good quantum numbers that allows you to identify where these blocks are. This is why what I'm getting at here is that a code is not just a subspace of a system philosophically, it's more than that. It's a whole protocol that allows you to sort of partition your Hilbert space and do active rounds of error correction. Right, so but getting back to the point of general qubit errors, let's look at a specific qubit error that's not a single qubit Pauli, a rotation, okay, around the z-axis. Well, I told you that this can be expanded. This is a 2x2 matrix, and there's 4 Pauli matrices, and it can be expanded as a linear combination of the Pauli matrices. In this case, it's the identity and something times sigma z. And so let's look at it here, how it acts on our logical state. So here is a superposition of 0, 1 logical, and 1 logical. It's going to, it's going to map us to a superposition of the original state with some coefficient and an error state here with some other coefficient. And if we expand these, then we get just nothing happened, and then we get something in the z error space over here. And now, when we measure our syndromes, when we measure our check operators to extract a syndrome, we get a collapse event, right? We identify either that we're either in this error space or that we're in the code space, depending on which eigenvalue we obtained. And that means that these coherences here have collapsed. And we're basically back to the same situation as we were if we either had no error or a single Pauli z error. Okay? Do you see why I'm saying that this is a situation where the collapse principle actually helps you? You're using a feature of quantum mechanics that the environment tries to use all the time to kill our quantum superpositions. But in this case, we're using it in a clever way to kill any detrimental effects of the environment that we may have thought we couldn't correct. Okay? So in this way, we can detect this error. Okay, so I thought this was really kind of one of the beautiful things about why error correction works, and maybe it's something that in the 90s they didn't think was very intuitive. So we're good on this? All right. So before I go to correctable codes that actually correct errors, I want to give you some general conditions on that you can use for testing whether a code detects or corrects certain errors. So as I was saying, general errors, first we'll do the detectable condition. And you can sort of phrase it as a combination of two things. The first is that the environment, so you can think of these noise operators as coming in from some malicious environment. The environment cannot distinguish the code words. If you have a noise operator or an error operator, you can safely assume that this is something the environment can measure. And if the environment can measure it, then it better not know which state you're in, 0, 1, or 0 logical or 1 logical, which means the expectation value of the two, in the two respective basis states, has to be equal. And the second part is that the environment better not, cause bit flips or corrupt your logical information, which means that it should not be able to connect distinct code words. So matrix elements that are off diagonal in the code word basis have to be 0. Okay? And now we can combine these two physical ideas into a nice, clean formula using the projection onto the code which is another way of defining a subspace of a vector space. This is just the outer products of all the logical states. And using this projection, we can show that an error is detectable if and only if, when you project it into the code space, it gives you identity on the code space, which is the projection. Now, before, we had here this coefficient is some arbitrary complex coefficient. It doesn't have to be 0. Before, it was 0, because our errors took us out of the code space into an orthogonal error space, which, if you multiply it by the projection on the code space, gives you 0, right? This was a sufficient condition. If you get out of the code space, you're detectable automatically. You're done. However, it's not necessary, because this condition says that if, say, this error does allow you to stay in the code space, then it better not do anything to the code words. Okay? So this coefficient not being 0, an example of that is here. Say we had 2 phase flips happen at the same time, and if we remember our logical 0 and 1 code words, it turns out that these 2 phase flips actually their eigenvectors are the code words with eigenvalue +1. Okay? Now, the eigenvalue here is the same for both code words, which means that this operator effectively doesn't do anything to the code words. It doesn't take you out, but it doesn't do anything either, so it's fine. We don't need to worry about it. It's as if an error didn't occur. Okay? And these operators are going to be important. Maybe you already know why, but specifically, this is more general than just escaping the code space. All right, now what about correctable? So errors now, some error set EJ, mapping to different error spaces are correctable if they are also detectable, and they give you the same effect on the code space. So the conditions now are for pairs of errors. So you can think of this as like the error space here and the error space here combined don't do anything to the code space. In other words, the errors undo each other. You can think of this as EJ undoing EK. And if it's successful in undoing, then you get identity. Okay? It needs to undo EK within the code space such that nothing happens within the code space. We already saw, yeah?
So this is for each error set?
Yes. We have an error set, call it cal E. For that error set to be correctable, for any pair of errors in the error set, this has to be true. So you form this matrix called an error correction matrix, QEC matrix, to see if things work out. We already saw this in the single qubit bit flip case. They were not correctable because they induced different effects on the code space, right? And so one of them did not undo the other. So this condition is sort of being phrased in the way that one of them is trying to undo the other. You can write the first qubit bit flip as the second qubit bit flip times a logical operation, times a logical bit flip. So this X sub L is something that induces a logical bit flip. And if we plug this in, this is E1, this is E2. So if we do E1 dagger E2, then we just get 2 bit flips combined, and that's the same as this logical operation because we just multiply this equation by IXII from both sides. We get a logical bit flip, which by definition connects 0 to 1 and 1 to 0. So this is equal to 1, which is otherwise known as not 0. So that's violating this condition, sort of this condition, because the errors, the product of errors, are connecting the 2 different code words. So these are conditions that you can do, and you can write a bunch of papers saying, here's a subspace, and it satisfies these conditions for this error. Okay? But again, this is only just to verify that in principle a code can correct things. It's not showing you how to correct things, and that's also important. Right? Okay, so let's take this probably to some of you simple code and generalize it and make contact with other codes that are actually correcting errors. Let's rewrite this and as follows in the plus minus basis. And if we do this, then, and if we simplify it, remember we had sort of pairs in the first two and the second two qubits. You can actually rewrite it like this. Tensor product of two Bell states for each of the two logical code words. And here the Bell states are defined, as like GHZ state for two qubits, right? And there's two copies of it. See what I'm getting at? You can generalize this. And you can view this as a combination or a concatenation of two different codes. In fact, two different repetition codes. So you can construct this code as follows. First, you encode in a stupid repetition code. Why is it stupid? Because majority vote doesn't work. If one of my bits flip, I can detect it, but I don't know what to do with it. Okay, but let's just do that and keep going. Now, we have our 0-1 logical basis. We change it to plus-minus basis to get, sorry, this should be a minus here, plus or minus, to get the plus-minus superpositions of these stupid repetition code words. And then we apply the repetition code again in this basis this time. Now we redundantly store the plus-plus and the minus-minus state. And this is precisely this 2-qubit code. So in this way, you're combining the repetition code against bit flips with the repetition code against phase flips to get this 4-qubit code. And this is why this can detect a single bit and phase error. And of course, you can generalize this by using multiple copies here and multiple copies here. These are two different knobs you can tune. And if you crank up each knob by 1, you get the famous Shor code. Okay? And this Shor code now has enough structure and enough error spaces to resolve all single qubit errors in a way that you can correct them and not just detect them. Okay? I'm not going to go into the detail of that because there's a ton of error spaces in there. The number of error spaces increases exponentially because the qubit dimension is increasing exponentially with the number of qubits. But you can just take my word for it that this now can correct errors. And more generally, you can obtain, by tuning M1 and M2, you get these nice generalized Shor codes, or also known as quantum parity codes. All right, let's look at another code that stems from the 4-qubit code. Recall the 4-qubit code words are as follows. And now remember our nice +1 eigenstate, eigenvalue operator, ZZII. The code words turn out to be part of the +1 eigenvalues eigensubspace of this operator. And there turns out to be a few other operators that have this thing as well. So operators IIZZ and XXXX satisfy this equation as well. If you look at the code words, you'll be able to convince yourself that this is true. Moreover, the three operators ZZII, IIZZ, and quadruple X commute with each other, if you remember your Pauli matrices. And these codes, these operators, they have inverses. Their inverses are in themselves. They multiply together. The multiplication is closed. Anyway, they generate a group. You guys know groups? Okay. A group is something that is defined using multiplication, such that multiplying two elements of the group gives you an element in the group. There's a distinct element that doesn't do anything in the group, and then every element has an inverse element. Every Pauli string has an inverse Pauli string. The identity is in here, and things close multiplication. So it's a group. This is a way of writing the group. So this is the actual group, okay? It's a set together with an operation. It's all the products of powers of these three operators, S1, S2, and S3. A short way of writing it is using these using what's called generators. These are the things whose products of powers generate or are able to express any element in the group. And this is called the stabilizer group. The stabilizer group of a code is the group of operators whose joint +1 eigenspace is the code. Okay? Each of these operators admits a +1 eigenspace, and the code forms a +1 eigensubspace of that +1 eigenspace. But if you add enough operators in there, the intersection of all of the +1 eigenspaces of these operators yields the code. So this is a concise way of defining, an alternative concise way of defining what's called as a stabilizer code. Instead of writing the actual code words, which you can imagine if I'm having 100 qubits might get a pretty long expression, I can just write it using the stabilizer group, or even more succinctly, the stabilizer generators of the group, which again are just defining the code space implicitly using their joint +1 eigen subspace. Okay? And for this code, the 4-qubit code, there's a certain notation that you can apply for this code and general stabilizer codes. NKD notation, this is the number of physical qubits, number of logical qubits, and what's called the distance. And the 4-qubit code is a 412 code. It encodes 1 logical qubit into 4 physical qubits, and its distance is 2, and the number of errors it can detect, or the errors on, it can detect errors on d-1 qubits. In this case, it can detect errors on 1 qubit. So this idea of using a group of operators with a joint +1 eigenvalue subspace is extremely useful for error correction because it not only defines a code, it also gives you a way to get the syndromes. Remember, when we were doing the repetition code, we had to measure some eigenvalues of some commuting set of operators. Well, guess what? This is precisely our commuting set of operators that we can measure to use to do rounds of error correction for this code. The stabilizer generators are precisely the check operators that we can use to decode this stabilizer code. Okay? So it gives us the code and it gives us how to do this, the error detection and correction. And this is also a very general idea. It works for many other things. All right? How do you do an error correction presentation without mentioning the surface code? I couldn't help it. So the 4-qubit code is actually also a surface code. And you can see this as follows. You can arrange the qubits, which are the red dots here, in a square geometry. And you can express the stabilizer generators by sort of drawing shapes that connect any pair or some set of dots. So within this square, you can write the quadruple X operator because it touches all 4 qubits. And then over here, you have these semicircles that are colored differently because that corresponds to Z, and they connect 2 dots which correspond to the dots in the support of this operator. Okay, so this is some tic-tac notation that now was written here in order to get you to think about how to generalize this. This naturally also generalizes in more ways than you ever wanted to know. For example, these are some cousins of this small code that are written in the same way. So here, the white circles are the physical qubits, and this is now part of this, what's called as a rotated surface code family. And then you can go nuts. So you can put it on a torus, get a toric code, and people have been, and continue to work on this type of code. This is precisely the thing Kitaev was discovering, or had discovered, and there's many deep connections here to condensed matter and anionic systems that I can't go into because I'm not, I'm going to talk about bosonic codes. So, to link to bosonic codes, we're going to do one more connection to what's called the binomial code. So let's look at the 4-qubit code again, and now let's take the binary bit string, the bit string label of each basis state, computational basis state, and add up all of its coordinates without doing mod 2 arithmetic. So if we do that, and then we remove duplicates, all these 4 zeros add up to 0, this adds up to 4, these 2 add up to 2, so we just get 2 here. We get the following states. What are these states? These states are labeled by non-negative integers. And this code can be embedded in what's called the Fock space of something that has many different names. You can call it an oscillator. You can call it a continuous variable system. And this is our first example of a continuous variable or bosonic code. So the Fock space here models excitations of a system that has, like photons or phonons, that has arbitrarily large numbers of excitations in principle. And what I want to get across here is that the spacing, the difference in the Hamming weight that was useful here to protect against bit flips remains useful here when we pick a different alphabet for our space. These are also spaced apart by 2, so changes or losses or gains in the occupation number of this system by 1, are they detectable or not? Detectable. And so this same logic that's done here in binary codes in Hamming space follows through to the various bases that I'm going to use to define bosonic codes in this larger infinite dimensional Hilbert space. I'm going to use several bases. I'm going to use the Fock space, and I'm going to use other bases that are now continuous. But the point is that there is still a notion of spacing and packing in these spaces such that bit flip type noise will not connect 2 different code words.
So can you explain the connection between the left?
Can I explain what?
What the connection between, like, how you get from the left-hand side?
So, right, so think of this as a vector of 4 coordinates and take the total, the sum of the coordinates. And then here, the sums here give you 2 and 2 and renormalize the state.
Yeah, but doesn't 2 contain 2 one thing?
Which one? This one?
No, the right 2 is equal superposition of both cases 2 1.
This one you're saying should be different.
So if isn't the state which reliable is 2 is equal superposition of both cases 2 1?
So, sorry, the Hilbert space I'm using here, the basis for it is defined by states that are labeled by non-negative integers, 0, 1, 2, 3, 4, 5, etc. And I'm mapping to this space by just taking the total of my multi-qubit state. Yeah.
But it's not 1 for 1.
It's not what?
Not 1 for 1.
It's not one-to-one mapping. No. Yeah. It's just a heuristic.
Okay.
This is the physicist in me, so speaking. So thanks. With that, I wanted to thank you guys for your attention. Yeah.
Yeah, maybe I'm getting from experience and taking notes, but the last code, if I'm losing one boson or getting one boson one into the I can use the problem and get 3.
Yep.
And if I gain a boson from 1, I still get 3. So it is like a non-retrievable code in that sense.
So one loss and one gain are not going to be simultaneously correctable, right? Just like the bit flips for the 4-qubit code, but they will be detectable.
They are detectable, yes.
Yes.
I mean, I don't know if I'm just getting a 3, I don't know.
Exactly. They're not correctable, but they are detectable. Yeah, you can correct one loss or one gain. I think I said or, but if I didn't, I'm sorry. Yep.
For code to be correctable, if it's like an equivalence, it's like sufficient and
Yes. Yeah.
because first example, when we looked at bit flip,
Yeah.
do 2 bit flips or then a behavior or another one, you don't cancel out.
Yeah. 2-bit flips are not correctable. Single bit flips are correct.
You said it's correctable if I can, if E and E vector are like canceling out each other, or are they considered the issue?
Oh, I see.
Like X and X vector which is X and just acting on verification I'm able to connect for a single.
Yeah, yeah. So here. So this is going to be XXI
Yeah, XIXJ,
or XIX, whatever. That takes you to the space here that's spanned by 101 and 010, right? and then this is 0, 0, 0, 1, 1, 1 space. So they miss each other.
Oh, so C,
Is 0.
it could be 0 also. Okay.
It can be, it doesn't have to be.
Oh, okay, that's what I'm talking
Yeah, like it's not 0 in this case with ZZII, but it doesn't do, ZZI doesn't do anything. But and sometimes it's also 0, because if you have different error spaces, this matrix, this CJK, for errors that are linearly independent often winds up being 0. You know, it's only the errors that do the same effect, that take you to the same error space that you have to worry about. Then you have to see if they undo each other. Okay.
Why is this Bosonic code comes before the continuous problem?
Yeah, okay. Yeah, I said I was going to use different bases to define define bosonic codes, and because there are different bases that you can use for your bosonic system. Because a bosonic mode is a separable or countably infinite Hilbert space, there exists a countably infinite basis for it, which is this Fock basis that I used. But I don't have to use that basis for the space. I can use other bases for the space that are continuous. Okay. My point here for this code was that there is still a notion of spacing in these other bases. That's the only point I was trying to get across. I guess the second point that you noticed is that continuous variable or bosonic codes can be digital, similarly to binary codes or qubit codes, because of the existence of this Fock space. But in the next lecture, I'll also give you some analog type codes that do use continuous numbers. Okay. Basically, you're right. There are many different manifestations of error correcting codes in a bosonic system, some of which are very much sort of not very continuous at all, like these digital binomial codes.
Okay.
Thanks.
Thank you very much.